all had many talks till this day by faculties, guests, speakers, and students. So in this series, we have today a talk on graph theory for organic chemists from Professor John F. Ogilvie, who is from two universities now, University of Costa Rica and Simon Fraser University.
So Professor Ogilvie did his bachelor's and master's in chemistry from the University of British Columbia in Canada. He did his MA in physical chemistry from the University of Cambridge, and following which he did his PhD in physical chemistry from the same place. Presently, he's a professor at the University of Costa Rica and Simon Fraser University. Professor Ogilvie has authored a monograph which is titled as rotational and vibrational spectroscopy for diatomic molecules, and he has also written a book which is available as an ebook, an interactive ebook, which is titled as Mathematics for Chemistry Using Some Computation Symbols. So today he will be talking to us about graph theory for organic chemists.
Well, good evening, everybody. I am suffering from sore throat, so I hope that you can understand me. I cannot speak very loudly, so we need this amplifier. Can you hear me? Can you hear me? Yes. All right, this is perhaps a slightly informal occasion, speaking to the Student Chemical Society, so perhaps I shall begin in a slightly informal manner. Many persons in India, while I've been here this past 2 weeks, have asked me, is this my first visit? And the answer is no. I was here 40 years ago, for various reasons. And then I went on, I had a round the world air ticket because I was going on sabbatical leave to Australia. And one of the students in the Canadian University, which I was teaching at that time, his name is Bajpai, arranged for me to give a lecture in the Baba Atomic Research Center, Bombay. So then when I went on to Australia, when I was in Australia, I managed to find a computer that has software for computer algebra. I had heard about that when I was in Canada, and I needed it for my research work on the spectrometry of diatomic molecules, but nobody knew about it in that location. But in the Australian National University, there is an IBM 36050 computer that had something called Formac on it. Now, in the early days of computing, there were two main languages. One was COBOL, which is commerce and business oriented language, and that had very good capabilities for handling files. But the arithmetic was very limited. You could not take the square root of a number with that software. And then there was Fortran, and Fortran had all the scientific and engineering functions that were needed in technical arithmetical computing. So IBM decided that they should have a combination of those two languages, and that was called PL1, Programming Language 1. Then they said, well, maybe we can have not only arithmetic programming and file handling, maybe we can have some algebraic capability. So they designed something called Formac, which was a formula manipulation compiler, which is a superset of PL1, and that had this algebraic capability. You can think of it as partly a word processor, right? And the arithmetic capability, so that teach the computer how to recognize key words like diff for derivative, right, or int, and so this sort of word processing capability was built into this format, PL1 format. Unfortunately, that computer, it was quite a good computer back in those days. It had all of 64K memory, 64 kilobytes. Now, you probably all have computers, and probably none of them has less than half a gigabyte, right, or 1 gigabyte or more. So 64K, and when it had this enormous PL1 plus format built out of it, there was very little left for a workspace. So I was unable to do much there. But in later years, I did manage to do some significant work with computer algebra for my research. And in the early 80s, I started to give lectures on this, the use of mathematical software for scientific purposes, chemical and physical purposes. And at the same time, I came to the opinion that this software could be useful in education, in the teaching of mathematics. Now, I gave some lectures on that in various places, and people said, oh, you know, that's very interesting. Maybe we can try that. Well, let's go back to the Middle Ages in Europe, when the Indian civilization was thriving in India. Europe was in the Dark Ages. But there were universities, and in the universities there were professors and lecturers. And this was before the time of printing. So they had handwritten books. And it was the job, the task of the lecturer to read this book to the students. And then they would discuss the contents. And so lecturer comes from the Latin for read, to read. Right? And then there's a professor. The professor was somebody who could write a book. So there were few professors but many lecturers. And that situation has continued to this day in some countries. For instance, in Australia and in Denmark, there are only 2 or 3 professors of chemistry, and the rest are just lecturers. And those professors are very distinguished chemists who have probably written books. So one of the difficulties of teaching a course on mathematics for chemistry students or mathematics for anybody is that one needs a book, a textbook. So about 20 years ago, my older brother said, why don't you write a book? And the result is what you see here. Mathematics for chemistry with symbolic computation. Now, this book has 2 parts. Part 1 is mathematics for chemistry. And that mathematics for chemistry contains the mathematics that a professor of chemistry would like his students to learn in courses that are typically given in a mathematics department. And so that goes through all of the mathematics from arithmetic up to differential and integral equations and statistics. And then part 2 is the mathematics of chemistry. And that is the topics in that part 2 are topics that are normally taught within chemistry courses. So chapter 9 is on chemical equilibrium. Chapter 10 is on group theory. Chapter 11 on graph theory. Chapter 12 on quantum mechanics, chemistry. Chapter 13, molecular spectrometry, which is the subject of my first book, as referred to the introduction. So today we're going to go through some parts of this chapter. I am the author of this, but I had great help from this student who is is from New Zealand originally. He took 2 years of chemistry and switched to computer science. I'm not sure whether the orbitals bring off chemistry or not. I'm not sure. I suspect they may play a part. But then he did his PhD in the University of Waterloo in Canada, in which maple was developed in the 1980s. And then he became a professor in Simon Fraser University in Vancouver, Canada. Now, let's begin. I'm just going to show you pictures, so you don't need to read the text very much, so I'll leave it at that magnification. I can make it larger, but then the diagrams don't fit very well. And this is a map of Königsberg in Prussia, which is actually east of present Poland on the Baltic Sea. König means king, and Berg means town, so this is equivalent to Kingston, and it was the seat of the Prussian royal family. And you can see there's a river here, the Prado River, that flows down here, and there are 2 islands in the river. And connecting the 2 sides of the river and the islands, there are 7 bridges. And the question that arose was, could one begin walking at a certain point in the town and cross all the bridges in one direction only and come back to the same point? And so this was debated by the people who had time to debate those things. And there was a famous mathematician called Leonhard Euler. The E in Euler is the same E that you use for exponential function. He proved that the problem has no solution by representing the problem in this form. So this is a graph. You saw the map of the city, partial map of the city. Now here's a graph. The 4 blue ovals represent the 4 parts of the town. So the 2 islands on the one side and the other side of the river. And the black lines represent the bridges between the 2 parts of the town, or the islands. So in the language of graph theory, we call each point here a vertex. That's the vertex on a triangle. And each line that connects 2 vertices is called an edge. So a graph consists of vertices and edges. So that was the diagram that Euler used to prove that it was impossible to do that walk, as I mentioned. Now here we have 2 graphs, just abstract graphs, and the one on the left here has 4 vertices, 1, 2, 3, 4, and 4 edges. And this graph is connected because all the points are connected, and it's unweighted and it's undirected. Now, in the graph on the right-hand side is a directed graph. You can see the arrows here, and that graph might represent the distribution of water in a town. So the water flows in one direction through the pipes. So this is a directed graph, and this is an undirected graph. And generally in chemistry, we're interested in undirected graphs. And the diagram composed of points and lines might hence represent a graph And that name was proposed by J.J. Sylvester in 1878. He was a mathematician in Cambridge. Here is a diagram of something that you might recognize. In Costa Rica, this is a sacred object because on Sunday morning, the men don't go to church, they go to watch the football match. And this